Hello and welcome to the third video series on chapter 15 on acid-base equilibria. So this is continuation of the CH103 lecture series. So in this section here, we're going to cover the last two topics, and that is the acid-base indicators and polyprotic acid titrations. So what is an indicator? An indicator basically is something that is used to indicate when you have reached the point of stoichiometric proportions in a reaction. So far, we've been looking at using indicator that changes color. But in this chapter, we've looked at the use of pH meter. So pH meter can monitor the pH, and then from the plot, which we call the titration curve, we can get the equivalence point. So in the acid-base indicator, it marks the endpoint. And notice that the term endpoint is used when there is a color change, and the equivalence point is used when we're looking at the actual stoichiometric proportions, which we tend to realize that when we use pH meter. So the pH meter really is a much more accurate indicator compared to the color indicator. So this is a typical titration setup. When you have an acid and a base titration, phenolphthalein is often used as an indicator. And phenolphthalein is actually colorless when it's in the acidic form, which is, that's the acidic form which is in the molecular acid. And then in the basic form, it is with the loss of a proton, it provides only the anion. So IN is used as a general form. So HIN is a general representation of an indicator. And what we are saying is that an indicator essentially is a very weak acid which has a proton in it and its conjugate. I mean, it's an ion in this case. So that's what we observe. In the acidic medium, you have colorless, and basic medium is the pink color. So that's the structure of phenolphthalein. It has 3 benzene rings connected to a central carbon here. So one of the benzene ring is actually carrying a functional group, carboxylate, and this is a hydroxyl group in the other 2 benzene ring. So this is the HIN form, which is the one that is present in acidic medium. And in the base form, the proton is lost. And where is the proton removed from? It is removed from this oxygen. So that's a proton that is removed. And that's what we get. So you notice that in this structure here, the ring, which is a resonance structure in the 3 rings, it becomes totally changed when we have one of these protons removed. You can see this structure is a series of alternate double bonds coming through the entire structure. And this conjugated system is what we often see in any compound that displays very intense color. So let's look at an example here. Bromothymol blue, an indicator with a Ka value of 1 times 10 to the power minus 7. Yellow, it is yellow in acid form and blue in the base form. All right, assume that a few drops of this indicator is placed in a strongly acidic solution if the solution is then titrated with NaOH, at what pH will the indicator color change be first visible? So let's look at this setup. So the Ka is 1 times 10 to the power minus 7, and that is the same, that is related to the concentration of the proton and the anion to the acid. So we're going to make an assumption here that the color change is visible when you have the ratio 1/10. Now 1/10 makes it a very simple ratio determination, and also it gives you a kind of a limit in terms of the limit in which this ratio system are going to be acting. So let's look at that. So we assume that we see the first hint of greenish in that when the solution contains 1 part blue and 10 part yellow, and that's what we are saying. In experimental, we actually see that, where you see this change in color. Okay, and then therefore we can carry out the substitution here. 1/10, which is the ratio of the two acid and its anion, and then you can find the value of H in this relationship. So find the value of H. It becomes, or it'll give you the value of 1 times 10 to the power minus 6, and the pH of that should be 6. So the first color change, the color change will be visible when you reach a pH of 6. Now we can also apply the Henderson-Hasselbalch equation in this calculation. So this is the Henderson-Hasselbalch form. pH is equal to pKa log of the concentration of the anion and the acid. And we know the Ka value, so we can bring that in. So given the ratio, it's conveniently substituted into that Henderson-Hasselbalch equation, and you get this value. Now, instead of solving, what are we looking at? The log of this number is a -1. 1/10 or 0.1 is -1. So you're looking at a pH is equal to pKa minus 1. All right, so if we look at the indicator once again, you see here that Ka is given here, and the pKa is 7. pH in which the color change occurs, it starts at 6. Now, when a basic solution is titrated, let's look at that. When a basic solution is titrated, the indicator HIN will initially exist as HIN. So if we consider the reverse of that setup, it will show the flip of this ratio, which is the value of the base will be higher. In this case, the base is the IN minus, will be higher. So it'd be 10/1. So let's do that sort of determination. pH is equal to pKa log 10/1. And this ratio here, log value of that, is a +1. So this is what we see. pH, when you approach this titration from the basic side, it'll be 8, which is 7.1. And if you approach it from the acidic side, is 6, which is 7 minus 1. So what do we get? So if we combine these two, this is essentially what we get. The useful pH range for bromothiamyl blue will be where the pKa is +1 or -1, which is 7 plus or minus 1. So what does that mean? What it means is that to select an ideal indicator for any titration, we're looking at a titration that will have the pH at equivalence point pretty much close to the pKa, and you can only work within that suitable range, that is a plus or minus 1 range of the pKa in order for the right or suitable indicator. So here you got a very nice table showing you the different indicators and the range of pH where they show the change in color. So crystal violet is from 0 to say 1.8. That's a pH. Crystal red, it's between 1 to 2. So in other words, if you have the end point of your titration occurring at that pH level between 1 and 2, this will be the suitable indicator. Now let's look at some indicator that we are familiar with, and that is phenolphthalein. Phenolphthalein, you see that the pH change range comes from about 8 to 10. So the pH at equivalence point that you want for this is ideally sitting between 8 and 10. So this range of pH indicators, this indicator of the titration common indicators, you'll see that these are more on the basic end, and this one that you see here are towards the acidic side of the titration. So question is, how do we choose an indicator? These are some general criteria or characteristics of indicator. The indicator and indicator endpoint and titration equivalence point needs to be as close as possible. So if you have a pKa of 8, then the pH at equivalence must be also close to 8. That's what it means. A good indicator produces a sharp endpoint during titration, so you need one that will show a very clear change in color at the endpoint. Now let's look at an example here. Consider the titration of 100 ml of 0.1 molar HCl and 0.1 molar NaOH. All right, so they have pretty much same concentration, and if you start with 100 ml, let's look at the changes to the indicator in general if we choose one indicator. Initially, in acidic solution, the indicator will have H-ion form. As OH are added, pH initially increases slowly and then rises rapidly at the equivalence point. So this is the equation for the ionization or dissociation of the indicator. So the anion, ion minus, indicator anions, are produced, and the color change can be observed using the criteria we've set from the previous discussion. So here we have the difference or the ratio of the two concentrations, where the onset of color change is said to be a factor of 10. So 1/10 in the ratio. So substitute that in, and we get pKa -1, because this ratio here will be a -1. Now let's look at the other side. Following this relationship, we can be used to find the pKa value of the indicator that changes color pH 7. So here we see that the pH is 7, and that's pKa -1, or this is what it is, 7. pKa -1 or a pKa 7 + 1. So that is the preferred range of indicator when you're looking at the pH of 7. Thus, an indicator with pKa of 8, which has the Ka 1/10⁻⁸, changes color from about 7, and also from the changes color at about 7. So this is ideal for making the endpoint for a strong acid, strong base titration. So the indicator color change will need to be sharp and occurring in addition of just a single drop of the titrant. So there is a wide choice of suitable indicators. The results will agree with 1 drop of titrant when the indicator is with endpoints that are as far apart as pH 5 and pH 9 are used. So if you look at this plot here, the endpoint is sitting here at the, this is the equivalence point. But notice where the change in color. The change in color can occur within this range pretty much with quite a high degree of accuracy in the monitoring the stoichiometric point. So that means you can use methyl red, because methyl red occurs exactly in the same region, and also phenolphthalein. Now, most of us know that this is what we often use, phenolphthalein. So that's still valid because you can see the change, the range of phenolphthalein from pH 10 to pH 8. That's when the color changes, and that's pretty much still in the region of this equivalence point. But alternatively, we can also use methyl red, and that should also work pretty much accurately. So what about in the titration of weak acids? The weaker the acid being titrated, the smaller the vertical area. So you don't see this very wide region in this equivalence point region. Although the equivalence point is here, but you see hardly any change occurs in this range. And that's why you have quite a broad selection of indicators that you can use. But when you come to a weak acid, the vertical area is a lot narrower. So your choice of indicator has got to be really very specific and unique to that region. So, for example, if you continue to consider the 2 for a weak acid and strong base, notice that the titration curve is not as sharp rise as we saw in the previous example for strong acid, strong base. And what we also see here, the methyl red is still sitting here, but methyl red region is way below the equivalence point. So in other words, if methyl red is used, your changing of color is well below what we would expect in equivalence point. So phenolphthalein, yes, it's still pretty much applicable to use in this, but not methyl red. So let's try this another example. So if you're titrating a weak acid, HA, 0.1 molar, with 0.1 molar sodium hydroxide. The stoichiometric point is known to occur at pH value approximately 10. So in other words, that's the equivalence point pH. Which of the following indicator acids would be best to use to mark the endpoint of this titration? Okay, so you're given these three values. Okay, so if you look at these values here, if it's a pH of 10, right, pH is equal to 10, right? So that means the pKa should be plus or minus 1 from the pH. That's where you're looking at the relationship. So the pH, if it's a pH of 10, you're looking at a pKa of plus or minus 1. So if the two are the same, pH and P, so you're looking at a pKa of 10 plus or minus 1. So essentially, you're looking at a pKa value in the region of 9 to 11. So if you look at these values here, Kas, this Ka here is for B, pKa is equal to 11. And this one will be pKa is equal to 8, 6, 14. So the right answer, or the best answer there, is this. All right, so now let's just finish up with the titration of polyprotic acid. And the example there is phosphoric. Phosphoric is a triprotic acid. So the first reaction of that will dissociate to give you H2PO4, and after H2PO4 minus, it'll dissociate to form HPO4 minus, and after H2PO4 minus, it'll dissociate to form PO4 minus. So you have those three different sets of equilibrium, and that is Ka1, A2, it's Ka3. So that's what we have looked at previously when we look at so what we want to look at here is essentially looking at the titration curve, because we are titrating this acid and the base. All right, so what will we get? Let me go straight into the curve here. So you see here in the plot of pH versus the volume of sodium hydroxide, you have the first equivalence point, which is the first proton removed, and then the second equivalence point when the second proton is removed, and then third equivalence point. So in other words, in a triprotic acid, you expect 3 equivalence points. And these are the major species that are present in this region. So in the first region, you see that H3, which is the fully undissociated acid, which is the molecular form, and the first proton left or removed. So here you have the second dissociated form in equilibrium with the one that is 2 protons removed. And then in the third region, you have the third proton removed from the last proton. So this is the two species that is involved in this third equilibrium relationship. Now, after that, then you're looking at just the excess base that is left over after the consumption of this ratio or these two acids, two anions in this mixture. Okay, so this is the triprotic. There are three equivalents, 1, 2, and 3, and these are the pHs at equivalence point. That's the first pH, second, and third. And now let me just highlight these pHs here, the midpoint of the equivalence, that is half of the equivalence point. So this one here, this is where pH is equal to pKa for the first, pH is equal to pKa, which is pKa2 of the second, and pH is equal to pKa of the third. So this is what we do expect when we are looking at multiprotic acid. Only one equivalence point when you're looking at a monoprotic acid. Diprotic, you're looking at two equivalent points, and triprotic, you're looking at three equivalent points. And the pH values at various points of the curve can be determined by using the pKa values. So that's an example of a diprotic acid. So you have two equivalent points. That's the first one here, and that's the second one here. And you're looking at the two regions of pH is equal to pKa. That's in the first plateau. pH is equal to, so right at the midpoint. So when you're looking at this value here, this is VE1. So this one here is VE2. That's the equivalent point. Equivalence point volume 1 and equivalence point volume 2. But half of that, that is between this and this, halfway is right here. That's where the ratio of the two concentrations of the conjugate base and the acid are equal, so pH is equal to pKa. And likewise, pH is equal to pKa. That's for pK2 here. All right, thank you. That brings to conclusion the lecture series, video series on chapter 15. Thank you.